What are you getting on the and then Juliana you
Asking for your own.
I want to go back. We're going to talk about dipoles. Can I have your attention, please, everyone? Dipoles and electric fields for continuous charge distribution. That's the goal for today. So let me go back to electric fields, and then I will mention the dipoles, and then I will do a torque on a dipole, and then continuous charge distribution. Okay? So electric fields. What's the symbol for an electric field?
E.
E. Good. And for a point charge, what's the electric field? So here is a charge, Q. That's the force for two charges. Electric field, you only have one charge. KQ. R squared. The direction, R hat. It's radially outward if it's positive, radially inward if it's a negative charge, right? This is the electric field due to a point charge, so I don't need this point charge anymore. K is, of course, 1 over 4 pi epsilon naught. And I emphasize this can be written as KQ over R cubed, and then the vector R. Okay, that's the electric field. Now, what's the significance of an electric field? So let's say the electric field at this point is in this direction. Here is the electric field, okay? Suppose we have an electric field, somebody produced an electric field for us, some charge produced an electric field for us, and that electric field happens to be in this direction, okay? Let me draw a few lines of this electric field. So let's say the electric field is just to the right. So don't worry about how we produce an electric field to the right. Suppose it just exists, it's to the right. Okay? Just like gravity is downward, right? So we're not going to worry about how it's produced, you're just told it's downward. Okay? So question 1, I have a plus charge, I place a plus charge in here of magnitude Q. The charge is Q, I place it in the electric field. So charge positive Q is placed in this electric field. What would the force on this charge be? I heard to the right? Yeah. Okay. And yes, that is correct. And what's the equation to get the force? Yes, it is the charge times the electric field. Good. So if it's a positive charge, Q is positive, a positive number times E will be a force in this direction. That's the force. Suppose now we put another charge, I put it with green, a minus charge. In what direction is the force on the minus charge?
Left.
To the left, because Q is minus, a negative number times a vector will flip the vector, so that vector will go this way. So F will be this way. All right? Good. Similar to, just again, if you're ever confused with the electric field and the charge, like as far as forces go, remember, think of charge, mass. Electric field, gravitational field, or G. What's the force if I place a mass M in G, in a gravitational field G? What's the force? Mg. QE, mg. Okay? Just remember that. Yes.
So in this situation, is E then negatively charged? Is E or is the field negatively charged or positively charged?
The field is pointing in this direction.
Okay, got it.
The question that you may ask, who is producing this electric field, right? There has to be some charges producing it. We're not worried about where they are or how they do it for now. We just know, yes, charges produce fields, and the charges may be somewhere here. We will get to how to produce a field to the right. We'll get to it at some point.
So it could be a positive charge.
It could also be negatives. Maybe you have negatives here. But let's not worry about that for now. Okay? For now, here's an electric field. It's to the right. You're just told it's to the right. Okay? Sounds good. So now we're going to remind ourselves of dipoles. before we do the torque on a dipole. So for dipoles, a dipole is a plus and a minus charge, right? So you have a plus charge and positive Q, and here is a charge that is negative, minus Q. They're just a plus and a minus. And the question is, in what direction is the dipole moment? In what direction does it point? What did you say? Yeah, I like that. Yeah, from the minus to the plus. Dipole moment P. Oh, okay. Yeah, what's the symbol for dipole moment? P. So P is equal to the charge times what? R. Times R or S. We call it S, right? S is a vector. S is this vector. S, the magnitude of S is just the distance between the two charges. That's the size of it. So basically, Q times the separation between the two charges. Its direction is just from the minus to the plus. Yes?
For the distance, is it from like the center of the charge or?
They're point charges, so they have size 0.
Sorry?
They're point charges, so I draw them big, but they're point. They're really tiny, so it doesn't matter.
Oh, I see.
Yeah, here I'm just exaggerating. If it's a ball of charge, yeah, it would be from the center of the ball.
Oh, I see.
But we'll worry about that later.
Okay.
Yeah. So that's that. So now, the torque on a dipole. So again, here's an electric field. An electric field, it's in this direction. I'll draw. Okay, that's the electric field. So, how do I know it's to the right? Somebody told us so. So the electric field is to the right. And I need a little more space. I'm going to cut down this. And I'm going to place a dipole in this electric field. Our dipole, here it is. Here is the plus. And here is the minus. Okay. That's our dipole. In what direction is the force on the right charge? On the positive charge.
Right.
To the right. Okay. So the force on this charge is going to be to the right. It's QE, and since it's positive, the force is going to be that way. Okay. In what direction is the force on the negative charge?
To the left.
To the left, because it's minus. Just like what we did. What's clockwise? The torque is going to be clockwise. So you expect them to rotate this way, clockwise. That's correct. So your two charges like this meter stick here, and somebody pulls on that end toward the wall, and somebody pulls here, so it will rotate about the center, right? Yeah. It will eventually flatten out, and when it reaches here, there is no longer, the torque will just be 0.
Ini kenapa torque di sini? Kamu ntar bakal gitu.
Yeah.
Oh, karena ini forcing to left, ini forcing to
If
left.
the
Jadi kayak
positive is here,
Like, yeah, if the negative is at the top and the positive is
So, maksudnya
yeah, like if you reverse it,
nyarinya susah.
then they wouldn't be anti-clockwise.
if the negative is there and the positive is there, yeah. Yes.
Because when it rotates.
Yeah. Yeah, it will, if the positive were, if this were positive, that were negative, it will go like this. Eventually, the positive would be here and the negative would be there. The dipole and the electric field would point in the same direction. Yeah.
What is separating charges?
Oh yeah, why are the two charges connected, right?
Yeah.
So we will pretend they are probably connected by a massless rod. In practice, maybe it's a bond, a chemical bond. Yeah. Good question. Yeah. So somebody maybe made them. Here's a meter stick, maybe it's massless. They place the plus here and a minus here. And we will not worry about how they are connected also. Good question. Okay, so the question is, how much is the torque? What's the torque? And we need to express the torque in terms of the dipole moment and the electric field. So notice they're going to rotate about this point, right? That's correct. So who can remind me, torque, what's the symbol? Tau, good. And what's the definition of torque? RF. So R cross F is the cross product between R and F. Cross product. R is a vector that points from the point of rotation to where the force is applied. So for example, this torque, we're going to, the torque would be due to the force of the minus and the force of the plus. So we would have this. The torque is going to be R plus crossed with F, the force of the plus charge, plus R minus crossed with F minus. And I'm going to now focus on these and what they are. Okay? R plus, I'm going to draw it. Again, R is a vector that points from the point of rotation to where the force is applied. Here's the point of rotation. And so the force is applied there, so this is R plus. Okay? This is R plus. That's R plus. So let's focus on this one. We'll worry about the minus in a moment. Okay? Worry about the minus in a moment. Now, and then I will worry about the minuses. So R plus. What can I say about R plus? If the distance between the two charges is S over 2, good. So it's 1/2 of S, or S over 2. In what direction does it point? In the same direction as S or different?
Same.
Same. So it's just the vector S divided by 2. It points in the same direction, it has half the size. Okay? How about the force? The force on the plus would be, yeah, the charge times the electric field. So Q times E. Good. We will now worry about the minus crossed with this one. I will draw, let's use red or blue. Good. How do I draw the vector R minus? Good. So this is R minus. From the point of rotation to where the force is applied. This is R minus. So how big is R minus? Okay, so you're ahead of me, so it's half the size of S, but it points in the opposite direction as S. So minus S. Good. Yeah. Now what's the force? Yeah. So Q times E, but Q is minus. Now, minus times minus is plus. So this term and this term are exactly the same, right? So when you add them, the half goes away, right? So you end up with, yeah, let's put torque. So you would just have what? Instead of half, you just have S cross QE, right? S cross QE. I'm going to move here. The Q, I would put it in front of the S, so it looks like this. QS crossed with E. Okay? What's QS?
P.
Yeah, that's P. QS is P. These two. Yeah. So minus times minus is plus. Yeah, but two minus signs, the constants in front, you can multiply them. So you have a minus times minus, that goes away, becomes a plus. What's left then is 1/2 of S and QE, right? But is this different from this? When you finally remove the minus sign. It's the same, right? So it's the same. So the half and the half, you just get twice. Yeah. Okay, so another half. So that is okay. So what it's saying is, if you put a dipole in an electric field, it will experience a torque until the dipole is aligned with the electric field. If they are aligned, what's the cross product of two vectors that are parallel? Zero. So there will be no more torque once it's aligned with the electric. Okay. So we're going to leave dipoles alone, and we're going to focus on continuous charge distribution. Yes.
So does that mean that the torque is variable based on how?
Yes. Yeah. The torque will vary based on the angle. Yeah. It's not a constant torque. Yes.
Sorry, could you explain about how QS is P is P power?
Q is the dipole moment. P is QS. Not power. It's. I know we recycled the letter P a few times. It was pressure, it was power, it was momentum. It's dipole. So continuous charge distributions. We can have point charges, right? But we can also spread charge over a line. Let's say somebody takes a charge Q, a whole charge Q, and then just spreads it over this line. So you take a charge Q, so let me write here, linear charge distribution. Let's say I have a line of length L, okay? The length is L, and I take a total charge Q, and I spread it over this line. So the charge density, or the linear charge density, is going to have the symbol lambda. That's linear charge density. That's linear charge density. And it's defined as this, just the total charge over the total length. So it is Q divided by L. Which should remind you of mu or lambda, depends on the textbook from the mechanics class you had, when you did ropes, and then like waves on a speed of waves on a rope was the square root of tension over mu. That was the speed of the wave on the rope. At some point, anyway, that concept was mass over length. In here, it's charge over length. Okay? It's called lambda. Does that make sense? I'm saying it because we're going to use it in a second. Now, no waves yet. So if I get half the length, so let's say this meter stick has a charge Q on it. Okay? The meter stick has charge Q on it. If I cut half the meter, how much Q do I have? Half Q. Good. And if I cut just 1 centimeter, how much of the Q I have? 100, because the meter has 100 centimeters. So the amount of charge I have is proportional to the length. Longer, more charge. If I have the whole length, I would have the whole charge. So in other words, let's say if this is length dx, there would be charge dq on here. How much is that dq? Well, it's, can you guess? dq is lambda times dx. So just the amount of charge you would have is proportional to the length. If dx is the whole length, then lambda times the whole length would just be q. So that's called linear charge density. Then there is surface charge density, or area charge density. So instead of spreading my charge over a length, I can paint the charge on an area. In that case, the question becomes, how much charge is there if I cut myself like a square centimeter or square inch? How much charge do I expect to be on there? So for area charge density, area charge density, charge over area. Oh, by the way, needless to say, linear charge density, the units would be coulombs per meter, right? Charge over length, coulombs per meter. For area charge density, the units would be coulombs per square meter. Yeah, meter square. And so we need to give it a symbol, and the symbol is, well, depends on the book. Our book uses the symbol, it says more or less standard, it's sigma. So sigma is the charge per unit of area. Sigma is the charge per unit of area. This one is lambda, right? Is the charge per unit of length. Now, so if you have charge over an area, so what happens if I cut myself like a little dA? Here's a dA. You just cut like a square centimeter of area dA. In that case, the amount of charge you would have in there would be dq is equal to, take a guess, sigma times what? dA. Yes, correct. Sigma times dA. And then finally, so in one dimension, it's Q charge over length. In two dimensions, it's charge over area. And then the next one would be volume. For three dimensions, it's the charge per unit of volume. Just like mass density, mass over volume. In this next case, we do charge over volume. So volume, charge, density. For that one, the symbol is rho. Rho, it is charge over volume. Charge over volume, and the units, of course, will be coulombs per cubic meter. This one we're going to need in the next chapter, but for these two we will need soon. Okay. All right, so with that said, we're going to do our first problem. The rest of today and probably a good chunk of next lecture are going to be finding the electric field due to different charge distributions. So if I have just a point charge, the electric field is kq over r squared, and I'm done. But if I have multiple charges, I need to add all the electric fields. So here is the first example. First example is going to be this. Here's the x-axis. Okay, here's the x-axis. And we're going to take like a rod or some meter stick maybe. And we're going to place the total charge on it is capital Q. And the length of this meter stick is going to be L. So the length, not meter stick I should say, of this rod. That's L. And the distance from here to here is X. Is that clear? The rod starts here and ends here. So there is charge. The charge is only on the rod. So there is charge only here. Okay, that's where the charge is. So that's where the charge is. And is the setup clear? So I have a rod. It has a total charge Q, the total length is L, which is to say, what's lambda in this case? Q over L. Good. Q over L. Good. So the question is this. We would like to find the electric field, the total electric field at this point, P, or red dot. So here's the question. Find So you can't say it's KQ over R squared. Why not? Yeah, so not the whole Q is at one spot. Some of the Q is close, and then, right, different parts are different distances. So if you say it's KQ over R squared, which R? You can't say it's the middle point either, because it's proportional to 1 over R squared, so the average is not going to be that. It's not going to be the midpoint. So we're going to divide this. Yeah, the idea is we will divide it into many little DQs. So we're going to think of the rod as this. So we're going to think of it as this. We're going to divide it into many little DQs. Here is one DQ, right? There is a DQ here. DQ. The distance from DQ to here is x. Okay? The distance is x. And this is dx. Okay, that's dx. And the distance from dq to here is x. Okay. Is that clear? So now, this dq is a point charge. That one I can say kq over r squared, and I need to sum up all those little kq's over r squared, or kdq over r squared. Okay. So, I'm going to write down the electric field due to one dq. I'm going to call it dE. What's the electric field due to just this dq? Due to just that dq. What's the electric field due to a point charge? It's k times what? Yeah, instead of q, we'll say dq for now. Over the distance squared. So how far is dq from here? Yeah, it's x, so x squared, right? R is x. So over x squared. And what's a unit vector? Because I need to multiply by r hat. Right, so k is k. Q is, I'm calling dq because that's the point charge. R is the distance from dq to the point, that's x. And then I need my r hat. A unit vector that points from dq to here. What's that unit vector? Huh? Yeah, it is I hat but with a minus sign because it points left. I hat with a minus sign. Yeah. Yeah. We're going to now write down what dq is in relation to lambda. So it's going to be this. Minus k. And then what did we say lambda dq is in with lambda? Lambda dx. Good. And then over x squared, and then I hat. And then lambda is what? Capital Q over L. Right? It's capital Q over L. So go here, dE. Minus k. Lambda is capital Q over L, so capital Q over L. We still have our dx. We have our x squared. We have the minus sign, and we have our I hat. The I hat I'm going to just write in front, just to until I integrate, and then I move it back to the back. So that's dE for one little dq. Well, dq's, they start here and they end there. Right? So we need to sum them up. So it's going to be this. E will be dE integrated. The minus, the I hat, the k, the q, and the L, they're all constants. So they stay in front. So minus I hat, k, the q, the L. And then I have my dx over x squared. Now my limits of integration, what should they be? X. From X naught, okay. To what?
L plus X naught.
Good. Or X naught. Yeah, L plus X naught plus. Yes, this is L. Okay. Now we need to do this integral. I'm going to use it here. What's the antiderivative of 1 over x squared? That'll be the derivative.
Negative 1 over x.
Yeah, the antiderivative is negative 1 over x. Right? When you integrate this, you get negative 1 over x. There is a minus waiting. So what do I get overall? Just plus. So I get I hat k q over L, and then I have 1 over x from x naught to x naught plus L. So we get I hat k q over L times 1 over x naught plus L minus 1 over x naught. Technically we're done, but we just need to simplify it a little bit. Okay, so I'm going to simplify. So I get I hat k q over L
The equation.
x naught plus L. And what does this simplify? We get x naught minus. You need the common denominator, right? Multiply them, and then what? X naught minus x naught plus L. So what does that simplify?
L.
Yeah, just minus L. Okay. And then the L cancel. And so we get the minus sign that's put in front. K and Q and x naught plus L. And then my I hat goes to the normal position. So that's E. That's the electric field due to a rod a certain distance from the left end of the rod. It makes sense. Does it make sense that the electric field is going to be negative, meaning pointing to the left? Yeah. If the charge is positive, it should produce an electric field away from itself. Right? What do positive charges do? Produce an electric field where? Just away. And if you're here, away means left. What if it were a negative charge? What direction should the field be? To the right. If it were negative, we would have a minus times minus plus, so it would just be to the right. So it makes sense. For all these calculations, we just assume the charge is positive. But if it's negative, you just put a minus sign. We're going to go to the next one. We're going to still do this rod, and then we're going to orient it differently. Yeah.
Oh, I think that was gonna be your question.
So you need to break the possible. The part charging positive, that would be nothing is then doing constant.
And then choose your x-axis to be along the rod. Your x-axis should always be along the rod. That's the easiest. I mean, you may ask, let's worry about more complicated ones later, but you can ask, what's the electric field not here, but let's say here. Yeah, in that case, yeah, you would have an X and a Y component. But let's do the next one, because it's going to be the next difficulty. And then we can do, we'll have more and more difficult problems. So here is the next problem. So please follow along. Same rod. Okay, it's going to be the same rod. And we're going to now make the center of the rod at the origin. So, I actually don't need, I just need this. Here is X. Here is Y. The rod is going to extend here. This is L over 2. And this is L over 2. Okay? That's the rod. And so this is the next example. rod of charge density lambda. So the charge density on the rod is lambda, and the question is, find the electric field at the following point. At where? Well, here. At this point. Let's say this point is a distance y above the middle of the rod. Okay. That's the electric field that we want to find. Find the electric field at this point. Okay. Again, we need to divide our rod into many little DQs. That's always the idea. Divide it into many DQs and then you will integrate. So here is a DQ. DQ. We're going to have a DQ here. This distance is x. Okay. That distance is x. The width of this little slice is dx, and the dq sits in there. And here's vector r. That's vector r. I'm going to ask you, I hope you're with me. Vector r. I would like you to tell me, or before you tell me, just think about it for a second. How can I write vector r in terms of x, y, I hat, and j hat? Take a moment, and then tell me what I would write with vector r in terms of x, y, and then I hat and j.
xi plus yi, or plus yj.
Okay, it's I hat plus y j hat, and then I heard something. Negative x I hat? I like that, yeah. So, yes, so we have to put a minus sign in y, because r takes you from here to here, it takes you backward the distance x, and upward the distance y, so there's the minus. Yes.
So when you're setting up the integral, are you just gonna multiply half of it by 2? Because otherwise the negative would freak out if you did that.
No, it would still be okay, because even if you're here,
Oh, yeah,
x
'cause the
itself
x will
is
be
negative.
negative,
Yeah,
yeah.
yeah. Yeah, so I want you to predict, before we do the integral, we will do the integral, okay? I want you to predict, in what direction is the electric field going to be? Up? I like that. Yeah, it's just gonna be the j hat direction. Why? So think about it. This charge here.